Humans have always attempted to understand the physical world. The ancient Greeks, over 2,300 years ago, arrived at insights which continue to shape the way we understand things. But it has been the discoveries of physics in the last 400 years that has truly revolutionized the way we understand our physical universe. Perhaps the most remarkable thing about physics is that some of the greatest insights have come from attempts to understand the simplest and most common everyday events. Who would have believed that our understanding of the solar system, stars, galaxies, and much more would come out of an attempt to understand why things fall? Aristotle, one of the greatest of the ancient Greek thinkers, believed that heavy objects fell to earth faster than lighter objects. Drop a stone and a feather at the same time and watch which one reaches the ground first. For almost 2,000 years, Aristotle's belief about falling things was accepted as fact. In the early 17th century, an Italian named Galileo wondered if it was true. Legend has it that an assistant climbed to the top of the Leaning Tower of Pisa and dropped 2 stones of differing weights, while Galileo stayed on the ground to observe what happened. He found that both stones hit the ground at exactly the same time. Whether Galileo actually dropped stones from the Tower of Pisa or not, he tested his idea by experimentation and observation, a process that is fundamental to science. For this reason alone, he is often credited with being the father of science. Galileo was able to calculate important information about falling bodies. He determined that as objects fall, the speed at which they fall changes at a constant rate. During the first second, the speed is 9.8 meters per second, and after the next second, the object falls at a rate of double that, or 19.6 meters per second, and so on. So the rate of acceleration, or change in velocity, per unit of time is a constant 9.8 meters per second per second. He went on to reduce his observations to a mathematical formula. The formula is change in velocity equals gt, or change in velocity equals acceleration multiplied by time. Galileo's explanation of the speed of falling bodies was a remarkable achievement, but one important element was missing. He did not know how to explain the force that was making this happen. Galileo's use of a mathematical formula to express his ideas is very significant. Mathematics has become the major analytical tool of physics, and virtually all of the significant insights in the discipline are expressed as formulas. In 1530, Nicholas Copernicus, a Polish astronomer, studied the solar system, and using mathematics, he concluded that the sun, rather than the earth, was the center of the universe. Johann Kepler, working around the time of Galileo, used mathematics to calculate the orbits of the planets around the sun. He discovered that their orbits were elliptical rather than circular, and went on to work out a detailed set of laws that described the behavior of the planets. By the middle of the 17th century, the work of Galileo, Kepler, and others had prepared the stage for the greatest scientist of the day, Isaac Newton. His synthesis has come to be called the first revolution in physics. Like Galileo, Newton's work was the result of an attempt to understand things that could be observed every day. Newton built on the work of Galileo and Kepler and came to the conclusion that the motion of falling bodies, the movement of planets, and in fact the movement of any object at any time was due to being acted upon by a force, a push or a pull. He worked out what he called the three laws of motion, which govern the movement of all objects at all times and in all circumstances. The first law states that an object's natural tendency is to continue what it is doing. If it is moving in a straight line at a constant speed, it will continue in a straight line unless acted upon by another force. It also states that an object at rest will remain at rest unless a force moves it. This is known as the principle of inertia. There are many examples of the first law. The space probe Pioneer 10 has been drifting through space for 35 years. A hockey puck sliding on the ice will keep on going. And this steel pipe won't move until the claw does its job.
T-minus 10 seconds. 9, 8, 7. Go from 8 inches. Start. 6, 5, 4.
An object's mass is a measure of its inertia. The greater the mass of an object, like the shuttle, the harder it is to move it or change its direction. Note that physicists use the term mass, or the total quantity of its matter, rather than weight, because in space, all objects are weightless, but they never lose their mass. The second law describes how an object accelerates or changes direction when a force is applied to it. The change depends on the magnitude of the net force. The second law also states that the acceleration due to a given force is always in the direction of the force. The mass of the object is also important. The larger the mass, the greater the force needed to make it accelerate or change direction. The second law can be written as F equals ma. This formula is saying that applied force, or F, equals mass times acceleration, ma. This formula is used to describe the motion of objects under all kinds of circumstances. If a ball is thrown horizontally, it will continue forever unless a force acts on it. The Earth's gravity is a force that pulls on the ball, and it falls to Earth in the direction it is traveling. Newton's third law of motion deals with interacting forces. It states that for every action, there is an equal and opposite reaction. The opposing forces of these two tug-of-war teams balance each other. The swimmer pushes off from the floating raft, propelling his body away from the raft, but also pushing the raft backwards. As the law states, for every action, there is an equal and opposite reaction. A book sitting on a table remains where it sits because the table pushes back with a force equal to the book's weight. This seems like a simple-minded idea, but an architect or engineer designing a building had better understand the third law of motion and ensure there is enough support to carry the weight, or the building will fall down. In the building of bridges, or any complicated structure where weight must be distributed, the calculation of net force is vital because it shows where the stress will be concentrated. This is calculated through vector analysis. Physicists use the term force in a special way to describe any action that affects the movement of an object. For example, a person paddling a canoe across a lake provides one source of force, but there can be others. The wind against the hull of the canoe is a force, and a current in the water yet another force. Together, all of these different forces combine to make up the net force, which determines the direction of the canoe. A force has both a direction and a magnitude, or strength. They are analyzed using vectors such as this one. In this example, there is a force from x to A and a second force from x to B. These two forces combine to result in a net force, x to C. On the surface of the Earth, friction plays an important role in influencing moving objects. Friction is a force parallel to the contacting surface between objects. If there were no friction, the balls on this pool table would roll forever. But without friction, this climber would not make it up the rock. When laws in physics are expressed, outside forces, like friction, are ignored. Galileo did this when he ignored the influence of air resistance on the dropping stones. And Newton did it when he ignored the influence of friction. Isaac Newton made many contributions to physics, but perhaps the most important was his explanation of gravitation, one of the fundamental forces in the universe. One story has it that he got the idea of gravitational forces when he saw an apple falling from a tree. Newton was the first to understand that gravitation was a universal force that influenced all objects, and that this force accounted for a variety of phenomena, from apples falling to Earth to the behavior of planets. Newton's second law of motion states that an object accelerates or changes direction when a force is applied to it. But if that force works on an apple at the top of a tall tree, could it also work on distant objects? If so, why doesn't the moon fall to Earth? The Earth's gravitational force pulls on the moon, just enough to change the moon's direction of travel. But the Earth is a ball, a sphere. The Earth's curvature is such that the moon never gets closer to the Earth, and it stays in its orbit. Newton's law of gravity says that the gravitational force between two objects is proportional to the quantity of their masses, and inversely proportional to the square of the distance between them. Newton had provided the explanation that had eluded Galileo as to why things on Earth fall down and why planets stay in orbit. The reason is the force called gravity. In order to solve these problems, Newton developed a new mathematical tool called calculus. Using calculus, Newton's followers were able to plot the motion of the planets and handle a whole new class of problems. In the 18th and 19th centuries, it seemed only a matter of time before the application of Newtonian physics would reveal all of the mysteries of the universe. It took a physicist by the name of Albert Einstein in the early 20th century to shatter that optimism. Einstein was a revolutionary thinker, and his theory of general relativity brought a new understanding to the concept of gravity. Einstein introduced the idea of a four-dimensional universe. The three dimensions of space are length, width, and height. And there is a fourth dimension, time. This is called the space-time continuum, one of the strangest and most difficult concepts to understand in modern physics. Einstein theorized that the mass of an object actually distorts space-time, much like the line vectors in this drawing. In his theory, planets orbit around the Sun because they are moving through the distortions of space-time that have been created by the mass of the Sun. Einstein published his theory of general relativity in 1915. At that time, it was believed that light had no mass and was unaffected by gravity. Einstein's theory predicted that light would be influenced by the distortion of space-time. In 1919, during an eclipse of the Sun, a group of astronomers were able to observe light from a distant star, which would normally be obscured by the Sun's bright rays. The star appeared to have shifted from its regular charted position. It seemed that the light from the star had bent as it skimmed close to the Sun. This confirmed Einstein's theory that the light rays simply follow the curvature of space-time caused by the mass of the Sun. Although Einstein's description of gravity is very different from Newton's, the two give almost identical results for the weak interactions of gravity at long distances. But for strong interactions, like predicting the orbit of Mercury, the planet closest to the Sun, Einstein's theory is more accurate. Einstein believed that the forces found in nature, which are gravity, electromagnetism, and the strong and weak nuclear forces, are all aspects of the same force. Physicists since Einstein's day continue to try to integrate these forces into one unified theory, in the belief that this will deepen our understanding of the universe. As yet, they have not been successful, but physics has come a long way from the time that Galileo measured the speed of falling bodies. Galileo is often called the father of science because he was the first to test his ideas by experimentation and observation. True or false? Galileo studied the rate of, or change in the velocity of a falling object. Copernicus concluded that the Earth was the center of the universe. True or false? Newton's first law of motion is sometimes called the principle of. The second law can be written as F equals ma, when applied force F equals mass, m, times acceleration, a. True or false? The third law of motion states, for every action, there is another action. True or false? Vector analysis is a means of analyzing different forces on an object. Together, these forces combine to make up force. Without friction, the balls on a pool table would roll forever. True or false? Newton was the first to understand that gravitation caused planets to follow irregular orbits. True or false? Einstein's general theory of relativity looks at the impact of gravitational force on